This is Lecture 22 in the FOA series of lectures on fiber optics. In this lecture, we're going to talk about mode power distribution in multimode fiber, demonstrate what modes look like, and show you how mandrel wraps work to control modal distribution. Single mode fiber, of course, has only one mode, which goes straight down the core of the fiber. Step index fiber has lots of modes, but they are controlled by bouncing back and forth between the core cladding boundary. It's graded index multimode fiber that we're interested in because the index profile of the core guides the modes through the fiber and makes each mode slightly different in the path length that it covers through the length of the fiber. But what do modes look like? Is there a way we can actually show what a mode looks like? Yes, there is. This is what happens when we put a visual fault locator in a multimode fiber. The light, of course, travels in many modes, and when it reaches the end of the fiber, the coherent laser light starts interfering between modes. Modes that are in phase become highly intense, more intense, and those that are out of phase become dark because the phasing out of phase cancels the light out and you get darkness. So here's what all the modes in a multimode fiber look like. And you can see there are hundreds of them. If we put a little bit of stress on the fiber, you'll see how the modes shift. You can see there's more shifting on the outside than on the inside. That's because the stress in an optical fiber occurs mainly in the higher order modes, the modes that travel on the outside of the core. So here's a perfect illustration of the way multimode fiber works. There's the modes, and there's the higher order modes being moved around by putting stress on the fiber. The modes carried in a graded index multimode fiber are dependent on the type of source that you use. For example, if you use a broad beam LED, you may put light in most of the modes in the core. But if you use a narrow, restricted launch, like a laser, even something as straightforward as a VCSEL, which is becoming more common now in fiber optics, you don't launch much light into the higher order modes. It's somewhere in between these two conditions that we try to set test conditions so that when we test a cable plant, we actually come to a compromise but have a standardized way of doing the test so that when different people make measurements, their measurements can be comparable. There are ways of controlling mode power distribution, and you can refer to the FOA website for information on building mode strippers, scramblers, and filters. The most popular way of doing it is using a mandrel wrap. This mandrel wrap method has been around for at least 2, maybe 3 decades. A mandrel wrap acts as both a mode scrambler and a mode filter, and it controls the modes by subtracting the modes in the outer layers of the core. It does that by putting stress on the fiber, and the stress mainly causes higher attenuation in the higher order modes. This is the method that is typically called for in testing specs, although there's a new way of doing it that's much more scientific. It's simply not proven yet, and that's called encircle flux. You can read more about that on the FOA website. Now let's try an experiment. Let's try to see if we can see what happens with a mandrel wrap. The same mandrel wrap that we use when we control the mode power distribution in multimode fiber for testing. Now notice that there's a significant amount of light still outside the second circle, but that the outer circle encompasses almost all the light. But watch what happens when we start wrapping the fiber around a mandrel. You can see all the modes changing as we're applying stress. But let's put the mandrel wrap in to this length of fiber, and we'll see what happens. Now, look how little light is outside the second circle. We've reduced the light in the higher order modes considerably. And that's exactly what the mandrel wrap is supposed to do. It's supposed to filter out higher order modes. If we take the wrap out, you can see that we now have considerably more light outside the second circle, and even some that goes outside the first circle. So that's the effect of a mandrel wrap. We're actually removing the higher order modes. And by doing this experiment with a visible light source, in this case a coherent laser that allows us to see the modes, we can actually see the effect of the mandrel wrap and how it affects the modes in a multimode optical fiber. So you can see the effect better, we'll look at alternating still photos of the mode pattern out of the end of the fiber without mandrel wrap and then with the mandrel wrap applied. Let's start without the mandrel wrap, which you see here, and now we'll alternate in images between with the mandrel wrap and no mandrel wrap. Now you can see the difference in the mode power distribution in the multimode graded index optical fiber. When we strip off the higher order modes with a controlled mandrel wrap, that mandrel wrap is basically the same as is being specified in a new, more scientific way as encircle flux, which you can read about on the FOA website. More technical information on mode power distribution and encircle flux and other important topics about fiber optics are on the FOA technical website, the FOA Online Reference Guide to Fiber Optics, on our website. We're the Fiber Optic Association, the professional society of fiber optics.